I'll begin with a word of prayer. Holy Father, we thank you for this time we have to be together. We thank you, Lord, that you're awesome, even if we're not. And we just pray that you'll be with us today, help us to glorify you in what we do, and just help us to understand a little bit more about matrix Lie groups and such, Lord. In your name we pray. Amen. So as you guys are aware, I have a cough. I found that these delicious coffee caramels are helpful. They make me stop coughing a little bit. Now, so last time we talked about, what's the Lie algebra, right? And so, basically, Lie algebra is L paired with a bracket, right? And the bracket is a mapping from the Lie algebra across the Lie algebra to the Lie algebra again. And if we're talking about a real Lie algebra, it's bilinear with respect to real. So we had what do we have? We had xy is equal to minus yx. And we had, of course, that cx plus y comma z is equal to c x z plus yz. All right. And then the other, so skew symmetric. This implies bilinearity, because if you have linearity in the first slot and you have antisymmetry, you can transfer linearity to the second slot. So without loss of generality, I can say skew symmetry, bilinearity, and then the thing that makes it an honest to goodness Lie algebra, and not just some multiplication or whatever, is this somewhat technical but important condition called the Jacobi identity. Now, so here we have cyclic. Basically, you just take x, y, z, and then cyclically permute it, keeping the bracket structure the same. That's the pattern I think about here, personally. You can think about however you like. There, of course, are other ways to remember this thing.
Just make sure it's 2 permutations.
So again, antisymmetry or skew symmetry, bilinearity, and Jacobi. And this, of course, is for C in the reals. Now, if we had a complex vector space, right, then we'd have C in the complexes, but everything else pretty much the same. All right, we defined the joint mapping and talked about how it allowed us to find a certain Lie algebra homomorphism from the Lie algebra. I guess we were also using the notation L equals to frac G last time too, right? Mm-hmm. Okay, fine. So we talked about how the what did we do last time? We were saying that the last thing we got to, big thing we got to, was what the adjoint gives us a mapping from what, from like frac G to GLG, right? Where we define add x equal to, well, let's say add x acting on y equal to xy. We proved that that was a Lie algebra homomorphism once we got our head screwed on straight. Mostly me, not you guys. But all right, so some fun facts that I remember from my course in the algebras. You can define, in fact, let's see here. Suppose you have suppose you have a vector space, all right? You want to define a bracket on it. You can uniquely define a bracket by specifying how the bracket works for every
basis on
let's see here. If you can verify the Jacobi identity holds for distinct triples in your algebra, then it follows that it extends to satisfy any vector. So in practice, when you check the Jacobi identity for an actual example, what you do is you just check distinct triples to make sure it's legit.
Like just different x, y, and z.
Mm-hmm. Okay. So like, for example, just to give you an example of how that works out, if you were to look at SL2 over the reals, that's a set of traceless, right? So it'd be like A and R2 by 2 such that the trace of A is equal to 0. Now, I'd like to use a standard notation, so if you'll forgive me, I need to take a second to hunt down a book. It's probably behind everything that you're in. I think you're going to have to stand up for a second. Unless it's over here. No? What are you looking for? I'm looking for my book, which is titled The Algebras.
Is it under a desk?
Yeah, I need to get up for that. Oops, that's okay. Shining, right? Must be it. I will find it. Because I had it. I just saw it. I saw it over here not long ago.
Wait, is the one called Lie groups?
Lee? No, I'm looking for, really looking for, the algebras by, Erdmann and Wilden and such. It's a little yellow book. I know that's terribly helpful.
I see the one by Bump.
Yeah, that one's Bump's Lee Group's books. That's I mean, yeah, that'll have everything I'm talking about in there. And you know what? That's not a bad idea. He might have what I'm looking for. Let me look. Well, it's not too crazy, actually. There also exists. You can sit back down.
I took the thing down. You can see it.
You might want to check the, you know. Oh man, he uses H, R, and L.
Yeah.
Everybody, the books I'm remembering use E, F, and G for this. Oh, whatever. Anyway, I think. Well, I could be wrong here, and if I'm wrong, I'm so sorry. Let's say E is equal to. No, it can't be that. All right, let's assume that H is H. H is equal to 1, 0, 0, minus 1. Oh, man. Stupid cough. 0, 1, 0, 0. G is equal to 0, 0, 1, 0. Now, it's fairly clear that these form a basis for the subspace of traceless. Now, he calls it H, R, and L in this Daniel Bump's Lie Group's book, but we'll ignore Mr. Bump. Well, I'll take his advice, but I'm going to lowercase it. But that's the notation that I'm remembering from some other past life in math. Okay, so here the bracket is actually a commutator bracket. So to show that this set of matrices actually forms a Lie algebra, it suffices to show that it would suffice to show that the Lie bracket of HF and G is closed back in again on HF and G. So like what happens when you look at the bracket of H and F? So we gotta compute these brackets. There's 3 ones to consider, right? So we got HF minus FH, we got HG minus GH, and we've got FG minus GF. Now, I'm going to do the top one. Daniel, you do the second one. Bradley, you do the third one. Okay? And then we'll collect our results. And don't calculate too fast. Don't make me look bad. Here. Got it. Ah! Curses. So what did you get for the, either of you get either one of these?
I found that it was 0.
I'm getting all zeros.
So you get H with G is 0,
Yeah. Yeah, check that again.
and what did you get F with G was? You got 0?
Yeah, I got.
Oh, no, it's not 0. It's,
Oh, no. Yep.
sign error. Okay, it's, negative 2G.
Minus 2 what?
G.
Minus 2G, alright. Now F with G might be 0.
No. I got. What did I get? That's not right. I'm getting the matrix 1, 1, 0, 0, or 1, negative 1, 0, 0.
Let's see, when I multiply
Check that.
F times G, the first thing I think gives me 1, 0, 0, 0.
Yeah.
Mhm.
And the second one gives me
0, 0, 0, 1.
0, 0, 0, 1. No.
Right, so it's
Yeah.
just H.
Put it in the wrong place. So yeah, 0, 0, 0, 1.
Cool.
So negative H.
H.
Or just H.
Yeah. So there you have it. The Lie bracket of any two things in the basis comes back to the basis again. So that's, I mean, part one, so at the moment all I've showed is that the bracket's closed on the subspace of traceless matrices, right? Now, of course, this is a terribly inefficient way to show that. You could easily show that by just saying, well, the trace of AB is the trace of AB minus the trace of BA,
Which is the same.
which is equal to the trace of AP minus the trace of AB, which is 0. Yeah. So yeah. So yeah. The commutator is traceless. In fact, that would seem to be true. What? I don't think that even matters. I didn't even use the trace of A and the trace of B is 0 here either. Right?
Yeah. That's
A fun qualifier question for Lie algebras is something like this. Explain why the commutator of A and B cannot be the identity. Because if the commutator of two matrices works out the other thing, it has to be traceless. But the identity is not traceless. The identity has trace n. Some of the diagonals just n. But anyway, that's a fun linear question. All right, so now we got to check the Jacobi identity. How many distinct triples are there in SL2 here? Trick question. There's only one distinct triple. There's 3 things. So you just got to check. Does
So if there were more for a group, then you would have to check all combinations.
right? If you had 4, then you'd be obligated to check 4. For example.
4 choose 3.
Yeah. So is this true? Let's see. FG is HH. GH was what?
Be 2G.
Yep, 2G. HF was
2F.
2F. There you have it.
Yeah.
These cancel. That's 0. By skew symmetry. So there you go. SL2, a set of traceless 2 by 2 real matrices, is in fact a Lie algebra in the abstract sense. It's good I have that poster right there. Otherwise, I would have just made eye contact with a certain professor and we would be having a conversation. Phew, it's close. All right. As you know, I am enough of a distraction already. I don't need more distraction. Okay, does this make sense anyway? So this is, I mean, in terms of formally verifying something as a Lie algebra, this is the kind of thing you can do.
So you only have to do with Jacobi, because everything else follows from that, or do we have to test by linearity as well?
Oh, I'm assuming bilinearity, basically. I'm just saying, suppose this is how you define the elements and then extend linearly, thinking of it as a formal system. Of course, I can just, I mean, this is a little bit special because it's also a sub-Lie algebra of just the larger GL2R, which is defined by commutator brackets. So technically, I can use a sub-Lie algebra test to show that it's a sub-Lie algebra more quickly. But I'm just thinking, if I think of it as a formal system, right? If you have these three elements, H, F, and G, that, I mean, set aside the 2x2 matrices, right? If you just dispense with the 2x2 matrices, suppose you have these abstract elements, H, F, and G, that satisfy these brackets, all right? Extend those linearly to an abstract vector space with real coefficients. And then you have a Lie algebra because it satisfies the Jacobi identity, independent of writing them specifically as 2x2 real matrices. I mean, you could set aside the 2x2 real matrix and from just the algebraic structure have a Lie algebra. Okay, so hey, while we're at it, what's the adjoint? What's the adjoint? We can look at the matrix of the adjoint. Like, think about basis. You know, HFG. Oh, you know what? Fine, FGH. I guess it just something feels better about that. I don't know if that's the standard one or not. But suppose you have basis FGH. You can ask, like, what's the matrix of the adjoint of F, right? And I guess I can say beta beta in my usual notation, right? So that would be the matrix formed by, you take the adjoint of F acting on F, take the beta coordinate of that, the adjoint of F, acting on G, beta coordinate of that, and the adjoint of F acting on H, beta coordinate of that. That would be the matrix with respect to the beta coordinate system by the usual linear algebra. That's what you got. You got F with F, well, that's 0. Adjoint, so F bracket G is H, right? FH is minus 2F, right? And so by the usual, so this gives me column 0, 0, 0. And let's see here, this gives me
0, 0, 1.
0, 1. This gives me
-2, 0.
minus 2, 0, 0. Yeah. And if you calculate, say, the adjoint, what would the adjoint of, let's see here, let's do the adjoint of G, what's that look like? If you don't mind, I'm going to skip the thing I wrote above and just write it down. So I think about G with F. GF gives me minus H, which is, then I think about G with G, 0, 0. Then I think about
G with H.
G with H, which gives me 2G, which is
Yeah.
all right. Oh, and now I got it. Now I got to do the add H while I'm at it. Sorry.
It's 4:00 p.m.
It's stupid of me to do this with you guys. This would have made a nice test question. Oh well.
Okay, find another example.
Find another example. Yeah, I guess I probably could do that. Let's see. Add H would be what?
This would be 2 zeros.
HF.
Which is 2F.
Oh, so it's 2, 0, 0. HG.
2, 0, -2, 0.
Yeah, let's see here.
HH is 0, 0, 0.
Okay. So then, for fun, we did. What did we prove last time? We proved that, like, the adjoint is a Lie algebra homomorphism, right? So what should happen if I take the commutator of these 3 by 3 matrices? Like, what should it be if I say that this one is, you know, well, let me not invent new names. Who needs new names? So what would happen if we calculate the adjoint of F times the adjoint of G minus the adjoint of G, the adjoint of F? What do you think we'll get? Let me try to do it.
You get 2.
Let's see here. First of all, adjoint G gives me 2, 0, 0. Adjoint G times F, oh, zeros. Adjoint G, looks like I get a 0, and a 2, right? And then adjoint G times, adjoint F times G rather, zeros. And then 0, 2, 0. And then, let's see here, joint F, so 0, 0, 0, 0, 0, 2, 0, 0, 2. Ah, cool, check that out. So this of course is 2 minus 2, and the 2's cancel. Which of course is what? That is the joint of H.
H. That's just a joint of H.
Yeah. And of course here I'm talking about the matrices, of course, but I mean, it's kind of easy for us to prove this thing, right? But when you actually look at what it means for specific examples, it can be very dizzying what it actually means. I mean, if you have like an 8-dimensional Lie algebra, this adjoint homomorphism, it's a statement about 8 by 8 matrices that represent the algebra in some way. So, whatever. So there's just a little bit, and I just thought it'd be good to do an example, so there it is. Now, there's something called structure constants, right? So definition, if your frac G is the span, let's say, of, I don't know, say Fi. Oh, yeah, okay. Well, maybe say Vi, that's my usual notation, Vi. I equals 1 to n. Then, if you define Vi, Vj, all right, to be equal to the sum over k of f I j k vk makes the fijk, which are elements of the reals or the complexes, right? Structure constants of the Lie algebra. These are basically, I mean, one way of thinking about Lie algebras is if you give me the structure constants, you've defined the Lie algebra. This is how physicists think about it. Physicists think in coordinates, right? So basically the structure constants uniquely define the Lie algebra because they tell you exactly how the bracket works on a basis, and then if you extend linearly, you get a Lie algebra, provided the structure constants have to satisfy certain conditions, right? Like at the level of the structure constants, what do the axioms of the algebra look like? I mean, you've got like, first of all, well, I mean, in our current notation, Fijk is equal to minus Fjik for all ijk. Okay, all of these are for all ijk, so let me skip the for all ijk. Stupidity. Right here. Let's see here, and then, linearity is assumed. There's nothing I could say about linearity at the level of structure constants. Basically, the point is you define it on a basis and extend linearly. So that's that. But Jacobi is something, right? Jacobi basically. So if I was to look at, say, Vi, Vj, Vk plus Vj, Vi, Vk. Goodness gracious. Vk, Vi. I can't do it. Let me get it right here. Vj,
VK.
Ki plus Vk, Vi, Vj. And let me put in my other brackets, which matter, of course. Let's see, so it'd be something like the sum over L and M. Let's see, this one, we'd have something like F I L F, goodness gracious, sorry. FILM. Oh, fine. Let me not try to do this all in one.
Yeah.
Let me actually do steps. Sorry, guys. So, like VI. So this one would be sum over, let's say, L of FJKL VL. And then similarly, VJ sum over L of FKIL VL. And then VK sum over L of FIJL VL. Worked myself into a corner. But it's okay, because I will use that to my advantage. Of course, these are supposed to be equal to 0. And so then you can pull out the sum over L. I used that on purpose. And then you'd have a sum over, let's say, M. I think I can see it from this step now. So this one would give me like F, right, I, L, M, F, J, K, L, plus F, J, L, M, F, K, I, L, plus F, K, L, M, F, I, J, L, VL. Not VL, excuse me, V what?
M.
M, yeah. And then, so this condition that, so of course you can strip off the sum over M, right? And then you just have a sum over L. So the condition becomes the sum over L of F, I, L, M, F, J, K, L, plus F, J, L, M, F, K, I, L, plus F, K, L, M, F, I, J, L. Equals to 0
For all M.
for all M, yeah. So you have M scalar identities as opposed to the vector Jacobi identity, which is just one vector equation, right? Basis independent. This is the horror, which definition of the algebra becomes in the language of like physicists. This kind of thing. Of course, if you're actually working with an example, it's not so bad. That's more to the point what you want, you know? Do you guys know any other examples of the algebras that are sort of common to your experience?
Earth. R3 with the cross product.
Very good. Yeah, that's the one I was thinking of. R3 with the cross product. So like, so the cross product is not associative. So if you have like V cross W cross, I don't know, out of letters, U. Now I feel bad for having written it then. But this doesn't make sense. However, if you do this, and then you add that actually does equal to 0. So in other words, the bracket of V and W equals to the cross product of V and W defines in the algebra. That in fact does satisfy the Jacobi identity. What are the structure constants with respect to the standard basis of R3? So like if I take in my notation xi hat, you know, x hat j, so the unit vectors in the I and j component directions, well that would be xi hat cross xj hat, you know. Well that's exactly the epsilon ijk xk hat. And I guess the sum, find sum k equals 1 to 3. So the antisymmetric symbol is in fact the structure constants for this particular Lie algebra, the R3 paired with the cross product. You could ask, so that's a three-dimensional Lie algebra, right? Real Lie algebra. SL2R is a real three-dimensional Lie algebra. Are these isomorphic Lie algebras? Would be a natural question to ask, right? In other words, is this Lie algebra and the one I wrote at the start of class, are these actually the same thing, just different notation in some sense? I'm not sure right off the top of my head.
You have to find a different basis. Right.
Yeah, my inclination would be to try to understand more about the structure of the algebras and try to maybe, yeah, of course, yeah, you can just look for an isomorphism and just try to attack it directly. That's one way. But if we knew more about ideals and such, like the ideal structure of the algebras, then maybe we could answer that question. I'm going to leave it as an open question for now. All right. So that's that. Now he also defines in here the how to complexify a real Lie algebra and obtain a complex Lie algebra. And if you look at that, that is exactly what I do in linear, where I talk about complexification. You know. He also mentions that you can form the direct sum Lie algebra. So like if you have G1 and G2 both Lie algebras, then you can form, if you look at, like, you can give G1 cross G2 of the algebra structure, and it's denoted G1 direct sum G2. In particular, the bracket is just this. If you do like bracket of pairs, say x1, x2, bracket with say y1, y2. All right, what's the definition?
Pairs of the brackets.
So it's like x1 with y1, right? And x2 with y2. You can, and it might be interesting to actually check this, I don't know. You can show that in fact this direct product actually does have the structure of the algebra. It satisfies the Jacobi and bilinearity, all the things we need. Now, you can of course think about this in terms of, if you think about this in terms of matrix Lie groups, right? Basically, this thing looks something like, so if I have, M1 and G1 and M2 and G2, then I can say M1 direct sum M2. And so as a matrix operation, what that means is like this. That would be in this matrix. A group like that. You just block diagonal sum of them like that. So for example, if M1 is a three-dimensionally algebra, or like if M1 is in the 3x3 matrices, if M2 is a 4x4 matrix, then M1 direct sum M2 is naturally interpreted as like a 3 plus 4 7x7 matrix. And you can easily see that if you take like the commutator of block diagonal matrices, right? Like if I have A, B, commutator with say CD like this, what I get is I get the commutator of AC like up here, and I get the commutator BD down here, which is exactly, let's say, in concert with our definition component-wise for the direct sum. So that's what it looks like in the matrix. He doesn't say much of that in here, but that's what's the matrix version of that. Now, complexification. How do you complexify a real algebra? Like, for example, I talked about SL2R here. What would the complexification of this be? So, let's say SL2R is equal to G, all right? Then GC would be the complex span of the basis FGH, all right? Basically, you just replace the coefficients with complex coefficients. And so, Poison. Oh no. I had to get some more poison. The ants at our house are really just, they're bold. They have resisted all sorts of chemical warfare thus far. I don't know, I need to take it to another level. Maybe fire. Not enough direct sunlight to use magnifying glasses, but. Alright, so, I mean, a typical thing in here would just look like complex, like C, do you understand what I mean, the complex linear combination of these? So then the question then, of course, is like, how do you define, for example, IF with G or whatever? Well, basically you just force the complex homogeneity, all right? That defines the bracket on the complexification. And again, you could technically look at it as in the same sense that Gauss looked at the pairs of real numbers as a complex number. You could put pairs of these really algebras and define I as multiplication on the pair that mimics the multiplication by I on a basis element. In particular, something like F is equal to, so A plus IB is defined to be IA minus B for all A and B in Lie algebra. I mean that's the heart of the relation. Now he says that there's tons of isomorphisms between the complexification. Like for example, he says that SLN, the complexification of what we're doing right now, he claims that this is going to be isomorphic to SL2C. And he gives a list of other perhaps less obvious isomorphisms. I think the fact that basically the complexification replaces the real coefficients with complex coefficients, right? So in my humble estimation, the fact that GLN the complexification of GLNR, the complexification of, I'm trying to say, these ones, I don't see as these ones really require much proof. I don't know. Maybe I'm wrong. I guess the proof is in the isomorphism. So what's the isomorphism? If it's so easy, I should be able to tell you the isomorphism, right? If it's so easy. These are not equal, these are isomorphisms, okay? So like what's the isomorphism? What's the isomorphism from, say, A plus IB? Oh.
I think it'd be few, or just,
Maybe it probably helps to look at these as pairs for a second here to make me feel like I actually did something. So look at the complexification as pairs just for a second. So the isomorphism is just that maps to this, right? And like if fine. If this is a real matrix and that's a real matrix, then this is a complex n by n matrix, so bam.
yeah.
And the traceless condition is also preserved because trace is linear. So that the fact that those isomorphisms are immediate from that one isomorphism. Anything else? Now what was the definition of little? What was little un? What's this? As a real Lie algebra. Oh, do you want to get one of the lights behind you? Just the top one. It'll make me feel more awake. It's not really needed for the camera, it's just for me. So I thought for sure you were the person who put that candy Lego halfway up the tower.
No, it wasn't me.
That was Lorenzo. How did she get up there? That's what I want to know. I mean, that's really quite a reach for her. She must have stood on a chair or something. I don't think I can reach that. Let's see here. Going back, what's UN? Excuse me. Oh. Find this big table of it's connected and how many components. I'm almost there. Heisenberg group. I guess it's the Lie algebra of big UN, right?
Yeah.
What's the Lie algebra of big UN? So UN, I guess it has to be, so this, we had things like what? A dagger, A equals to the identity, right?
Mm-hmm.
So if you differentiate this, and you look at something like A equals to e to the TB, right? That's our custom. Then that would give you something like B dagger plus B equals to 0. So looks to me like UN is skew Hermitian.
Right.
Skew Hermitian. So he says that the complexification of these guys is isomorphic to, what was it? I lost my place again. He says that's also isomorphic to GLNC. Interesting, right? But well, I mean, UN was a really subalgebra of the complex n by n matrices, right? There's a little bit more going on here. I guess that kind of makes sense. I mean, so if this is a, I think I can. So, I mean, the question then, of course, is like something like this. If you have psi of, say, b plus ic, and here we have b dagger is equal to minus b, right? And c dagger is equal to minus c, because these are in UN, right? Supposed to be able to map that to sort of like a generic n by n complex matrix.
Mm-hmm. Do you use the direct sum?
Well, I don't know. I don't know what the mapping is. Does he tell us here?
What page are we on?
Page 58. He leaves some of these as exercises, so he might not have it in here. Aha! He says, if X is any complex matrix, he writes, oh, it's that trick again. Basically, his point is, if you have X in GLNC, well, you can write it. So he goes the other way. It's more convenient. You can rewrite this as 1/2 X minus X dagger. I think his star is the Hermitian conjugate. It's the conjugate transpose. Or does he actually have conjugate there? I
It
don't know.
has I over 2I. I don't know. What...
He says complex. He says UN. If a complex matrix, then they're both skew. What's his star mean? Is the question? Yeah.
I don't remember him ever using that notation.
What is the star? My own personal experience, stars are sometimes bars, and bars are sometimes stars, and sometimes stars and bars are daggers.
Stars and...
So, yeah. Well, he says self-adjoint means A star is equal to A. To me, that says that A star is conjugate transpose. Which I write dagger. Okay. Is there an I here?
There is an
Yeah,
I.
there's an I there.
Well,
Not there, but outside.
it's like I times 1 over 2I.
Which makes no sense to me. Why would it be that?
Where's the I?
He has an I outside,
On the outside of the
parentheses.
parentheses.
Outside parentheses?
Yeah.
Yeah.
So,
I think there must be something weird going on there.
Well, because he's got...
read it again to me. So it's, I've lost my place. I'm sorry, guys.
It's
And I just say page 58?
it's I parentheses X plus X bar or X star over 2I.
Okay, so the I's cancel, right?
Right.
And you're just left with 1/2 X plus 1/2 X, which gives you X. And then minus 1/2 X dagger plus 1/2 X dagger. The point is that this
It's gonna...
and this, these are both in UN. Because they're skew Hermitian. If you take the conjugate, if you take the dagger of these, get minus what you started with. If you take the dagger of this, remember it's a conjugate transpose. So it makes this go minus, and this is actually this is just a Hermitian matrix. Like Hermitian would be H dagger equals to H, all right? So like that is Hermitian. But if you take I times any Hermitian matrix, you get I conjugate H dagger, which of course is minus I H dagger, which is minus IH. Sorry, H is Hermitian. So if you take a Hermitian matrix divided or multiplied by I, it's skew Hermitian. So the point is, both of these things are in UN, and that's just a complex linear combination of them. That means the complexification of UN is naturally identified with a complex n by n matrix. And he makes an interesting point here, which is that while it is true that you have GLNC as isomorphic to GLNR complexified or UNC complexified, he says something that's slightly disconcerting to me. Where is it? Do you know what I'm talking about, Daniel?
Yeah, U of N is not isomorphic to GLN of R.
Yeah.
So last, or
Oh, I guess the point is their complexifications are isomorphic, but they themselves are not isomorphic. So it's kind of an interesting pattern there. Anyway, I love this complexification stuff, and I'd like to think more about like this notion of complexification. How does it play out over our study of algebras? Not so much for complexification, but say for algebraification, like generalizations of this notion of complexification, how to study it. Something I'd like to understand more. Now, that brings us to chapter 3, which is on the Baker-Campbell-Hausdorff formula. And so he does a great job of motivating it in section 3.1. He's like, the fundamental question, the critical result is this: if you have G and H matrix Lie groups with Lie algebras frac G and frac H, and suppose G is simply connected, then if you have a Lie algebra homomorphism little phi, there exists a unique Lie group homomorphism big phi, such that phi of the exponential of x is equal to the exponential of little phi of x. So there's this intertwining relation between...
It looks a lot like the add stuff, the adjoint.
Yes, it does, indeed. And in fact, the proof of this is going to involve, that add gets involved, yes. Absolutely. He says this result's extremely important because it implies if G is simply connected, there's a natural one-to-one correspondence between the representations of G, all right? So, again, this phi, what's the deal here? Phi is a group homomorphism G to H. Little phi is a Lie algebra homomorphism from frac G to frac H. Okay? So what's he say here? He says there's a natural correspondence between representations of G, right, and representations of the Lie algebra. Because remember, a representation of G is a group homomorphism of a particular type. Basically, a representation is a homomorphism into a model space. The model space that we usually have in mind is matrices. So like phi, capital Phi would be mapping from this abstract Lie group into a set of matrix Lie groups or something like that, that has a set of suitably sized n by n matrices that allows an isomorphic or homomorphic image rather of G to be found within it, so that the abstract group operation of G just becomes simple matrix multiplication in the group image, in the homomorphic group image. And likewise, for lowercase phi, a representation of the Lie algebra becomes, in the case that we're thinking about a representation, it becomes a set of matrices of particular size whose commutator bracket has the same structure as a Lie algebra as the original. Well, at least it has a homomorphic, at least, all right, homomorphic copy of the Lie algebra frac G within the matrices. So this abstract notion of into H, or these H's become, matrices of particular type when we think about representations. And what this equation here says is that there's a connection between the group representation and the Lie algebra representation, just related by exponentiation. And as he mentions, this is very important because this kind of representation theory is kind of scary, but this over here is pretty well defined stuff. Like there is a systematic machine to just knock down what are possible representations of a given Lie algebra. Like there's a well-defined mathematical machine to deal with representations of Lie algebras. It's
Can't we?
eigenvalues and eigenvectors of a generalized sort, of some sort or another.
Because aren't we dealing with matrices on the right side always? And then.
Yeah, I guess if we accept the context of this book, everything is matrices pretty much, right? But
Unless it doesn't have to be matrices, though.
the point is, the structure of the algebra is more amenable to techniques of vector spaces,
Right.
whereas Lie groups, well, I mean, contrast the difference in, like, even the adjoint. You know, the adjoint for the Lie algebra is like your commutator bracket, right?
Yeah.
The adjoint in the Lie group is like conjugation or something, and you know, I mean, it's anyway. They're you know, each side has something that's simpler than the other. I mean, to be honest, and so he points out that the trouble, and so he says basically what his next point is to be like he is, and his idea is, well, if that's what you want, you should use it as a definition. I mean, that's a deep idea within mathematics. If you know, if a theorem you work really hard to prove and it contains within it all of these different results that are interesting, by golly, that theorem ought to become the definition. Because assuming that theorem is to assume all those things, and that could be a very powerful principle of theory building. You know, think about topology. Oh, sorry. But I mean, there's this very greedy definition of topology, which basically summarizes the three most penultimate observations about this whole family of abstract analytical examples, which is that the arbitrary union of open sets is open, and the finite intersection of closed sets is closed, and what the other thing is, oh goodness gracious.
The whole set and the
Okay, the whole set and the empty set. I think that's more like a logical necessity as opposed to a interesting feature of examples. But those first two things are sort of just generic observations about all examples. So it's maybe that's not the best example of this kind of greedy definition making, but now he says the proof of this result is given in Vardarjan. I'm probably saying that wrong. It uses the Frobenius theorem, which you guys may remember from last semester, which is both hard to understand and hard to prove. I will agree with that. That is one of the banes of my existence in advanced calculus, is finding better ways of culling down Frobenius theorem and making it understandable. I'm not there yet. That is a battle I'm still fighting. It's a battle I might lose. Some years.
You don't lose it until you die. You haven't succeeded.
Oh, yeah, I'm trying not to die. So here, so let's see here. But he says he replaces this Frobenius proof instead with the Baker-Campbell-Hausdorff proof. But his ultimate goal is not Baker-Campbell-Hausdorff. His ultimate goal is to basically establish this relation between group and algebra representations. All right. Because chapter 3 is just a way station to chapters 4, 5, and 6, which are on representation theory, right? All right, so now he says, but basically, you know, this is, but you know, getting back to it, basically he wants phi. Let's just write it down again. Phi of e to the x to be equal to e to the phi x, right? So basically, he wants this to become. He'd like for this to be a definition of what? He'd like this to define phi for a given Lie algebra homomorphism, right?